Good morning, everyone. Welcome to the first talk in functional analysis and the operator series session. And the speaker is Xiao Xiong from Harbin Institute of Technology. He is an expert in functional analysis and operator algebras, particularly in analysis on von Neumann algebras, noncommutative LP spaces. Today, he is going to talk on spectral asymptotics of pseudo-differential operators with application in NC geometry. Please join me in welcoming Professor Xiong.
Okay, thanks very much for Joran's introduction. And I'd like also thank the organizers for giving me this opportunity to share my work. So this is about the application of noncommutative analysis to noncommutative geometry. So as you know, in the classical case, the connection between noncommutative analysis and between analysis and geometry is very close. And one important tool of this connection is so-called pseudo-differential operator. So today I'm going to share to tell you that this connection is still exists in the non-commutative setting. So I will explain our result about the spectral asymptotic and tell you that how this is how this can be applied to Alan Kohm's non-commutative geometry. Okay, let me begin with the very classical pseudo-differential operator theory. So you can view it as in the field of harmonic analysis. So symbols are smooth functions which satisfy this kind of a decay relation. So with this symbol, we can use the Fourier transform to define the pseudo-differential operator. So inside this integral, you can see that if our symbol sigma depends only on x, then it is a Fourier multiplet, because you see that you have a function u, you take the Fourier transform, and then you multiply by a function sigma, and then you take the inverse Fourier transform. So this is the very definition of, of Fourier multiplet. But on the other hand, if our sigma depends only on x, then we can just take it out. Then here we do nothing to u. So then it is a pointwise multiplication. So these are two extreme cases of pseudo-differential operator. But we will come back to this point later about how to understand pseudo-differential operator in this way. Okay, so here an example about this is like a differential operator. In this case, the symbol of this derivative d becomes is nothing but the function cosine to the power alpha. So this is a very basic example of pseudo-differential operator. So today we are going to talk about non-commutative setting. So we can of course we can do it this way. So imagine that we are giving a function, a good enough function, u, but takes value in some Banach space. In this case, to make this integral make sense, so we have to we can assume that our symbol takes value in the bounded in the space of bounded linear operators on this Banach space. So in this case, we understand this integral in the way that we first act every sigma on this Fourier transform or u, and then we still take the inverse Fourier transform to get back. So, but this is a very general setting of operator valued pseudo differential operator. But still, we can understand it in a special case, which is where we take the Banach space as the L1 plus L infinity, and then we take the symbol inside the polynomial algebra M. So here M is a polynomial algebra, and we assume that we have a good enough trace on this polynomial algebra, and also this L1 is defined with respect to this trace. So in this case, we adapted the definition of symbol in this way. So here, because our sigma is text value in the polynomial algebra, which we simply replace the absolute value by the norm, by the operator norm of the function. And in this way, we can define pseudo differential operator in this also with the same integration, with the same formula. But here I just want to recall that inside this integral, the noncommutativity appears, because now our u takes value in some polynomial algebra, and also sigma takes values in some polynomial algebra. Then you cannot commute. They don't commute. But of course, if you are not familiar with this kind of polynomial setting, you can imagine that this M is some matrix algebra. For example, this M you can imagine it uh, as an algebra of n by n matrices. And if you don't even be interested in this setting, you can just go back to the very classical setting. In this way, for example, this norm can be replaced by the absolute value, and then all this setting will go back to the very classical setting of pseudo differential operator theory. But the motivation we do this is that we would like to develop the theory of a pseudo differential operator in this non-commutative setting, because in this way we hope we could be able to consider the non-commutative geometry and some real non-commutative manifold. So this was our motivation, and this is why we developed this so-called non-commutative pseudo theory. Okay, let's move on. So here are two theories about symbol calculus, because as you know, even in the classical case, if we are giving a pseudo differential operator, if we take the adjoint of this pseudo differential operator, then we will get another pseudo differential operator. But even in this case, the symbol of this new pseudo differential operator is very difficult to be calculated. So, for example, even in the classical case, if we want to calculate the new symbol by the original symbol, then we have to do some asymptotic formula, do some asymptotic expansion of this sigma. So this is also the case in the non-commutative setting. So the symbol of the adjoint operator is expand in this way, and also the symbol of composition has also to be expand in this way. So here, we have to take the derivatives of the symbols sigma 1 and sigma 2, and then we have to do the linear combination of sigma 1 and sigma 2, and then we can get the asymptotic expansion formula for this sigma 3 for this new compensation operator. Okay, so another thing is about abundance. So we have an order m of every symbol sigma. So if this order m not positive, then we are able to show that the pseudo differential operator is bounded on L2. But not if we have a phenomenon algebra m, then we have to cancel L2 of m here. So this means we have our noncommutative pseudo differential operator is also bounded on L2 tensor F2. But here we have a very easy observation is that we can, so this phenomenon algebra is large, but here we can refine it in this way. We can prove that, we can show that this pseudo differential operator belongs to this tensor product of phenomenon algebra. So here so this phenomenon algebra, or this is B of L2 and RD tensor B of L2 and M. So this algebra is very large, but with some easy argument, we can show that the the pseudo differential operator belongs to B of L2, but tensor just the phenomenon algebra M. Phenomenon algebra M is of course much smaller than the bounded, much smaller than B or L2 or M. Okay, so this is not difficult to show, but this will be very important in our in our next context. This is because that we will have to when we define Riemann zeta function of the operator, we will have to do the functional calculus of our operator, of the pseudo differential operator, and then we have to take the trace of the complex power of m. Knowing that the operator belongs to this smaller algebra will give us convenience to first doing the functional calculus, and then to take the tensor trace with respect to this phenomenon algebra. Okay, we will come back to this point later. Okay, here is the definition of smaller family of phenomenon of pseudo differential operator. So this here we call the classical n-valued symbol. If our symbol, if this symbol admit this asymptotic expansion. So here psi is smooth enough, and sigma, this sigma, the sigma on the right hand side is homogeneous with respect to the variable psi. In this case, the leading term, of course, it is the largest term, will be called the principal symbol of the operator. So here I have the two examples, of course, two very important examples. One is called the Bessel potential, and another is risk potential. So, of course, in harmonic analysis, we can understand them as Fourier, but as I just begin with this, I said that uh, Fourier multiplier are also a special case of pseudo-differential operator. Okay, so this page I I we talk about simple calculus. So firstly, I like to introduce to you a theorem about simple calculus. But as you can see that inside this theorem, there's nothing about simple calculus. So it looks very strange. But let's first repeat the theorem. So we are given two algebras, A1 and A2, and we also have two representations which represent these two algebra into the same hyperspace. And we assume that they are unital. We assume at least one of them is commutative. And we require that the commutator of these A1 elements in A1 and elements in A2 are compact. We also require that if this linear combination of A and B compact, then we must have that the algebraic tensor product is 0. In we assume this 3, then the result is that there exists a star isomorphism. I denote by symbol. Sim. This is abbreviative for symbol. Then we have this. The map is defined. Then the map satisfies this two conditions. These two. Okay. So here you only the last statement is about symbol. But let me explain this. Let's understand this theorem this way. Then I think you may have a feeling how this is called simple calculus. So imagine that our H is L2, for example, L2 of torus and d-dimensional torus. This H is L2, and we can represent the algebra of continuous functions on torus to this L2 just by pointwise multiplication. So this keep in mind that this pi 1 is twice multiplication, and pi 2 is Fourier multiplication. So still H is L2 on torus, and then A2 is A2. We can take it as continuous functions on the unit sphere But and then because we are talking about so here we are talking about zero order pseudo differential operators. So we just have to take A2 as the functions on the unit sphere, but not on the dual of the torus, which is the group of integral or integers. So here A2 is the continuous functions on the unit sphere. In this way, pi 1 is pointwise multiplication, pi 2 is Fourier multiplication, and of course, because we can view these pi elements in A1 as zero order pseudo differential operator. we can also view the element here as a zero order, so the differential operator. Then we do the commutator. Then the simple calculus formula will tell us that this commutator is also a pseudo differential operator, but of the -1. So in this sense, this is compact. And also the third assumption is to assume that inside this construction we have to use the quotient map from B or H to the quotient space of B or H quotient the compact operator. So in this setting we can at least we can link this theorem to the theorem of simple calculus and so the differential operators. Okay, so but this theorem uh, is good only for zero order pseudo differential operator. So we hope that we can do it for abstract. We hope we can do it for arbitrary m order pseudo differential operator. At least we hope that if we are given a pseudo differential operator of the m, then we hope we can do the simple calculus to do the complex power of p. And also we hope the complex power of p is linked to the complex power of the symbol. Okay, so in order to do this, we need to, firstly, we need to do the functional calculus and the operator. This is done by the Dunford integral. So this integration is along this gamma from here and to some to the unit to some to the sphere to this circle, and then along this circle to the negative part, and then go along the x to the minus infinity. Okay, in order to make this integration meaningful, the first thing we have to assume that for every lambda along this gamma, we have to make this a good operator, say a bounded operator. In order to do this, we can assume that this lambda inside this gamma is not in the spectrum of the operator P. And secondly, we have to assume that the image part, the real part to be negative. To fulfill these 2 points, we can I remark here. Firstly, we need to assume that the operator P is positive enough, say strictly positive. If it is strictly positive, so here we take the radial to be 1/2 of this row. Then we can make this part. We can make this integral convergence in some sense. And another thing is that we didn't talk about positive integer, but here positive integer is it just be defined in a very usual way. For example, if p is positive, if the operator is positive, then we can define positive integer, positive power this way, and then for other complex number, we can just separate it into 2 parts. One part is the positive part, and another part is the complex part, but with a part smaller enough. Okay, so this is about the 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 functional calculus, the complex power of the operator. The complex power of a symbol can be done in this way. We can assume the ellipticity of the operator. It's the ellipticity, if we just look at the scalar valued case, we can just define this. We can just assume that the for pointwise the symbol is large enough. But here with some uniform constant c. But in the operator value case, we have to assume simultaneously this assumption. This in at least in self-adjoint case, these two is equivalent to this one. So in this case, we are able to do the functional calculus for the symbols. Okay, so yeah, so this allows to do functional calculus for the symbols. So after finishing the definitions, we are able to introduce our result about the about the about our the the complex power. Firstly, we can find a good enough symbol, a good enough pseudo differential operator B. B is constructed by the reservant of the of P. So, but the final result is that the difference between these two operators is good enough, saying that it is holomorphic on this area, and of course it is operator value. It takes the value in the pseudo differential operator of this order. So this is the structure theorem. With this structure theorem, we have to show that our the complex power of our pseudo differential operator P is also good enough inside uh, the order is m times z. And we have, with this theorem, we are able to show that we are able to do the to link, to connect the functional, the symbol of the functional calculus and the functional calculus of the symbol. So we are able to connect. And of course, it will this structure theory as well as the corollary will be important when we try to calculate the trace of the complex power.
Could you recall what is the meaning of C in front of psi?
C. So here, psi means pseudo. So C means that because we are assuming that P is good enough, P is classical. P has the yes, P has a very good expansion. Yes, yes. Okay, okay. Okay. Let's continue. So this is the first part of my talk. So next, let's move to noncommutative geometry. So it is given by a Fredholm module with so-called spectral triple. The triple is firstly the triple consistent of three elements. First, it is the algebra, which is represented on a Hilbert space. And secondly, we have a good enough operator, which is the abstract elliptic operator, which is self-adjoint, the square is 1, and more importantly, the commutator. Because now we are doing the commutator and the Hilbert space. So the triple requires that the commutator is compact. So this is the setting. And inside this setting, we have a definition of quantum derivative as well as a quantum integration. So this is derivative, this is integration. So the derivative makes every bounded element on the algebra to a compact operator, which is defined by df. So this df, if it is an operator on H, so we can understand it as infinite semial, because in the on a Hilbert space, if we talk about infinite semial, it is different from the concept of infinite semial in the very classical case. So in the operator setting, infinite semial means an operator is very small outside a finite dimensional space. So here the infinite semial is nothing but a compact operator. So here, so I just want to explain that this is an infinite semial, which is nothing but a compact operator. And also the integration. The integration is because it is defined, it is some kind of a positive linear operator. But this is given by Dix-Meer trees. So let's continue to explain the definition of Dix-Meer trees here. So we have the concept of small enough operator, infinite semial operator. So which is a compact operator. Of course, we can measure the size of a compact operator by the eigenvalue or singular value of the operator. So I didn't give the definition of the Schatten class, but the Schatten class you can just view it as the order of the infinite semial. So Schatten class, for example here, the Schatten class, it means that the eigenvalues, or the singular values of the functions is decayed of order 1. So for example, imagine that we have a diagonal matrix. The element in the it is 1, 1 over 2, 1 over 3, blah blah, 1 over n. Then it is an infinite semial operator. It is a compact operator inside this Schatten class. So given this Schatten class, we would like to define an integral. But in the very classical case, integral is a positive linear functional on, say, L infinity or L1 or something. But here, the quantum integration is a trace. It is a trace on this class of order 1 infinite semials, or in other words, it is a trace on the idea of S infinity 1 infinity. So with this in mind, it is not easy to find a way to define good to define a good enough function as infinity. It is given by this formula. So here, this omega, it is the thing. It has to be the singular part of L infinity joint, or the dual of L infinity. Because as you know, the dual of L infinity is not L1. It is larger than L1. You can there are two parts of the dual of infinity. Normal part is L1, and the single part is the other part. So here we have to make this omega as the single part of L infinity, or the dual of L infinity. So this is also the why people call this Dix-Meer trace as the singular trace, because this omega here is the singular part. But in our case, we if this limit exists, then the Dix-Meer trace of this A is nothing but the limit of the limit here. So also this is how this coincides with our title, asymptotic limit, or spectral asymptotic limit of an operator A. It is because it by definition it gives a Dix-Meer trace of an operator. Okay. So here let me introduce the question raised by Alan Kuhn when inside his 70th birthday ceremony in Shanghai. So he asked that for a pseudo-differential operator of some negative order. This D means the dimensional. So here this order is very special. It is minus D, and here as I have just explained, when we have a pseudo-differential operator, we hope to calculate the Dix-Meer trace, or calculate the Dix-Meer trace, and the result turns out to be the integral of the highest order, or you can say the principal order, principal symbol of the pseudo-differential operator. So here the integral is taken inside the uh, unit unit cotangent bundle of this as manifold. So this is Cohn's trace formula, and Cohn's question is that as I put here in red, Cohn asked is it possible to prove directly the asymptotic formula, but without using the tools like extended limit or Banach limit. This was the question, and we're able to answer the question in this two situation. The first situation is that we look at the very classical Euclidean space, and also the second is so-called quantum toric. But if you're not interested in quantum, you can still imagine that you have a Yo-yo toric, yo-yo d-dimensional flat toric. In these two settings, we are able to show that if we are given a zero order pseudo-differential operator, if we are given a zero order, then we can calculate the spectral asymptotic limit by the LD norm, or the symbol of the pseudo-differential operator. So this is to result answering the previous question. So here I'd like to talk maybe one word about the proof. The proof is that, imagine that we have a torus. We have a D torus. In this case, this operator, at least if we don't look at this P, this potential, the the eigenvalues of this potential is very easy to calculate, right? So the eigenvectors are this e to the I are the orthogonal basis. So in this case, the proof of this formula is very straightforward because we can just count the eigenvalues on those, like for every integer m, we take the length of this m, and then we take the negative power of this one. So this way we can calculate this. And I like to also explain why we need the compactly support here. This is because that, imagine that we do not have this part here, then then this part is not compact and RD. It is not like in an torus. It is compact. Okay, so this is these are the only two cases we knew before, because these two cases the spectrum can be calculated directly. Okay, so next, before moving to our result, I like to give this dictionary about single value value of an operator. So in the very classical case, when we talk about infinite dimensional variable, we can measure the size. We can measure the size by the order, and then the functions are in LP space or in LP infinity, also called weak LP. So in the quantum case, or at least in the previous two results, we are looking at operators on some Hilbert space, say L2 on RD or L2 on TD. So in that case, when we look at a compact operator, then the limit is 0, and the concept compact is corresponds to infinitesimal in the very critical case. And then we take this. This is what I haven't put on the slide. It is called Shelton class or weak Shelton class. They are the quantity to measure the size of an operator or an compact operator. So in that case, X means, as we have explained, it is defined by the asymptotic limit of an operator. So what we are going to do is that we will not just look at compact operator, and we will not look at the space of Shelton class, but some space of LP and the tensor product of M. So here still, if you are not interested in general phenomenon algebra, if you just look at a scale case, then this LP is nothing but this SP, and then this will coincide. But if there is some phenomenon algebra here, then we have to do it this way. Okay, so in order to give our final result, we need these two definitions. The first one is the Riemann Z function or an operator or a pseudo differential operator. So it is doing in this way. So firstly, when we are given a pseudo differential operator, then we take the complex power, and then in order, so here I'm free. So this is not that important, but just with phi here, we have a phi here. This will make this integral convergent. This is the main point. And so the red part, so here I have two red equality. So these are definition. But this blue one, this is not definition. This is just done by direct calculation, because we have a very concrete operator here. This operator is a integral operator value integral operator. As an integral operator, we can calculate the trace this way. But just be careful that the trace here, the capital T here means the trace on this larger on this tensor algebra. Still, if we ignore this M, then it is trace on this BOI2. Okay. Sorry?
The tensor product is the tensor product in the category of Riemann algebras.
Yes. So here, if I don't put this bar here, this means the algebraic one. If I put a bar here, I take the yes, or yeah, or in other, or equivalently, I take the Weik's-Stark closure. Yeah. Okay, so this is the result about the zeta function. So this zeta function, these two zeta function admit the meromorphic continuation to the whole complex plane. And the rightmost simple pole is located at the point D over M. And we can calculate the residue in this way. The residue is calculated this way. So how can we get this result? We just recall our structure theory about the difference of these two operators. So this operator is good enough. This is smooth enough. So in order to look at the meromorphic continuation of this one, we just have to look. We just have to analyze analyze the simple pole of this function. This will give us the result. And okay, what next? Next, I will skip this part, but I will come back to this paragraph later. But let me show you the last result. The last result state that the asymptotic limit of this P of this pseudo differential operator is constructed. This is calculated this way. The reason is that we have this Tabrian theorem, which states that if we know that if we know the simple pole of this function, then we know the asymptotic limit of this f, of this capital F here. So in order to get the result on the next page, we just need to assume that this capital, we just need to take this capital F as the spectrum projection of the function of this part. Yeah, I think this is my final result in this talk. So just some sentence about about this theorem. So firstly, here we have some fundamental algebra here. So in this way, we can that this is a version in the type 2 of noncommutative geometry. And secondly, so here we don't need to assume this P to be compact. So if this M is trivial, then it is indeed compact. But if this M is not trivial, then this is not Shelton class, but non-commutative LP space on some larger polynomial algebra. So in this case, it is not compact. Well, we can call it tau compact because it is. We can say that we may say that it is compact with respect to this part, but not compact with respect to this part. And also here, this P is not not to be assumed to have some ellipticity. Just we need it to be negative order. Okay, so I stop here. Thank you very much.
Okay, thanks for the very nice talk. Is there any questions?
So the usual definition of the Dixmuir trace, at least the old definition, involves some axiom of choice things like the ultra filters and things like that. And it seems that you avoided this altogether. Is it correct? So
I use directly the result. I mean, for example, in our definition, in this definition, so the requirement you mentioned will force this A will force the Dixmuir trace in this formula. So what I want to explain is that in the very definition given by Dixmuir, so he had to do it in the way you mentioned, but it turned out that the Dixmuir trace is given by the.
Yeah, so you restrict. So
yes, some.
Dixmuir defines this for all operators, and you restrict it to S1 infinity, and this that's why you avoid using.
Yes, that's correct. So, for example, in this very special case, the Dixmuir trace is just calculated this way. Yeah.
Thank you.
Is there any other questions or comments?
So you mentioned that one can generalize this to type 2.
Yes.
And are there any surprises, or does it work more or less the same?
I think if we if we view it this way, I think just as I put here, it the difference is clear. It's written here. So here we have to we use this definition to do the thing. I think the point here in my talk is, or in my the last result is that we don't have to to look at the the eigenvalues point one by one, but we just do it in a as in a general way. I think it is I think it is a standard way to I mean to get the final result. Yeah.
Okay. Other questions? And then let's thank speaker again.
Thank you.